Okay, so last time we looked at these notes, we got about halfway through, so I'm going to kind of go through this first part kind of quickly, just as a recap. So this unit, we're talking about thermal energy. So thermal is talking about heat. And so it's another form of energy. So it's measured in joules, just like all your other forms of energy. And again, kinetic molecular theory is what it's all based on. So whenever you're thinking about something, think about kinetic molecular theory. So that's talking about how everything's made out of atoms. And these atoms are kind of jiggling or moving in place in a solid. And those such move more and more as you become a liquid and gas and so on. So whenever you're thinking about these different processes that we're talking about, if it doesn't make any sense, just think about little molecules moving, and then cold would be they're moving slow, hot is they're moving fast. So this is the definition of those three things. So hopefully you got those last time. These are the three temperature scales that were pretty commonly used in the world. Again, we're going to focus mostly on Celsius and Kelvin in here. Here's your equations to convert from Celsius to Fahrenheit, and Fahrenheit to Kelvin, or sorry, Celsius to Kelvin. As you guys probably learned last week, heat is the transfer of energy. It flows from hot objects to cold objects, not in the reverse direction. So if you got your power turned off last week, you might have noticed that you were the only warm thing around. So one of those things that you can do is you can bundle up with blankets or coats to help retain your own heat so that you don't flow all of your heat to the surroundings. And so, again, this is the definition of thermodynamics. This is heat transformation of mechanical energy. There are three forms, three methods of heat transfer: conduction, convection, radiation. Typically, we think of conduction as heat transfer through a solid, direct contact. Convection is heat transfer through a liquid or a gas. So convection, like hot air rises, cold air sinks. So you may have noticed if you had, if you have a two-story house and your power got turned off, you might notice that the upstairs is typically warmer than downstairs. And then radiation, heat transfer through electromagnetic waves. That's how the sun melts all the ice and snow. These next slides talk about conduction, convection, radiation very specifically, but we already talked about this. I'm going to kind of skip through all this. Conduction, convection, radiation. Specific heat, this is pretty close to where we ended, so I'm going to kind of pick up here. Specific heat is the amount of energy required to raise the temperature of a material by 1 temperature unit. So because of that definition, we can have different numbers depending on what you're looking at. So specific heat is talking about every particular material has a different amount of specific heat because it's made of different molecules. And that number also depends on what temperature scale you're looking at. So for example, it gives us water is 4,186 joules per kilogram Kelvin, or 4.186 joules per gram degrees Celsius. So it's the same number, but just changes based on our unit. So if you're looking at specific heat, things that have low specific heat capacities are things that are difficult to heat and cool. Or sorry, low specific heat are easy to heat and cool, and things with high specific heat are difficult to heat and cool. Because if it has a high specific heat, like water was 4,186 joules, you need 4,000 joules of energy just to raise the temperature by 1 degree. Right? So it's difficult to heat or cool water. So low specific heat is a good conductor, high specific heat is a good insulator. So here's our equation for, or that contains specific heat. And it says Q equals mc delta T. So Q is our symbol for heat. Its units are joules. So it's just another form of energy. So you think about like kinetic energy, potential energy, this is heat energy. M is obviously mass. C sub P is specific heat, and remember that sub P, it's not always going to be sub P, it's just, that's going to be your subscript to describe whatever material you're looking at. So like C sub W would be specific heat of water, C sub A would be like specific heat of aluminum or whatnot. And then delta T is our change in temperature, okay? It can be Celsius or Kelvin. We're going to try to stick mostly to Kelvin in this class. But delta T can be either of those because they have the same size scale. It cannot be Fahrenheit. Otherwise things get real different. But that's the basic formula. And so, I'll ask you questions about how to solve different things in the formula, like MC, delta T. I could ask, find the heat, change this amount or whatnot. So let's look at an example here. So we have a 0.4 kilogram block of metal absorbs 7,016 joules of heat as its temperature changes from 20 to 32 degrees Celsius. Calculate the specific heat capacity. So when we're looking at this, try not to really trip y'all up. So you'll notice that here we've got a mass, here we've got energy, and here we've got two temperatures, right? And it wants us to calculate the specific heat for this particular metal. So it doesn't tell us what the metal is, so I'm just probably going to write CP. But let's go ahead and write down what we got. So we got 0.4, so mass is 0.4 kilograms. The heat, Q, is 7,016 joules. And the temperature change is going to be final minus initial, right? So final temperature minus initial temperature. So in this case, the final temperature is 32, and the initial is 20. So that gives me a temperature change of 12 degrees Celsius. Okay? And it wants us to calculate the specific heat capacity. CP. So we have our formula, Q equals MC delta T. So we have to plug in and then solve for C sub P. Okay. Q is, Q equals MC delta T. So Q is 7,016. M is 0.4. C sub P is what we're looking for. And then delta T is 12 degrees Celsius. Kilograms, degrees Celsius. Okay. So in order to do this, the first thing I would do is take that 0.4 and the 12 and go ahead and multiply those together. Right there, on the same side. So 0.4 and 12. 7, 16 joules on this side. And I get 4.8 kilogram degrees Celsius times C sub P. Okay, so what's the opposite of multiplication? Division. So I'll divide both sides by 4.8. Degrees Celsius. So that'll cancel. So C sub P is whatever that is. 1461.67. So it would have, well, these units here. So joules per kilogram degrees Celsius. If we look at our choices here, so obviously this one is rounded. And that's our answer. So, again, as with every problem, first thing you need to do is identify what you know, what again, I don't think the math is too hard, but if you can't identify which equation, you're going to be stuck. And so that's the number one thing, students, you guys need to know is how to identify your equation. That's what the first step is all about, is writing down what you know, what you're looking for. Because that will give you a hint of which equation to use. All right. Do you have any questions about that? Okay. So, in which direction does the heat energy flow to put a warm beverage in a cold water? Obviously flows from hot to cold, so the warm beverage will get cold because the heat will flow from hot to cold. So here, I think it's neat to look at the molecular level. Remember that stuff about the kinetic molecular theory. In a hot beverage, those molecules are going to be moving a lot faster than, say, the cold water. And even the molecules in the can are going to be moving a lot faster than the water. And so what's happening here is you're transferring energy through collisions. And you can see that, like, the molecules in the can are moving faster, so they hit the can, so it makes them move faster. Then they hit the water molecules, which makes them move faster. And because you're transferring energy like this, when the hot can, when these velocities here transfer, then this stuff is left going slower. So we say the heat moves from hot to cold. Newton's law of cooling, there's not really any questions about this directly. The biggest thing that most people need to realize about Newton's law of cooling is the rate at which an object cools is directly proportional to the difference in the temperature between the object and its surroundings. So, for instance here, what this is showing is that if you have an object that's very warm, it's like 100 degrees Celsius, like boiling water, it cools very rapidly at first, but then decreases as that temperature decreases. And so, for example, if you have like a hot cup of coffee, let's say that it's at 100 degrees Celsius, like the boiling temperature of water, and they hand that to you, if it's just, let's say in a non-insulated cup, just like a regular cup, it will very quickly cool from, say, the 100 degrees closer to room temperature. Room temperature is, around like 20 degrees Celsius. And so, this is time in seconds, okay? So, here it's saying it'll go from like about 100 degrees to about 70. It'll drop 30 degrees Celsius in the first 15 seconds. Then after the first 30 seconds, it'll be down to 50 degrees Celsius. So it will have lost half of its temperature in the first 30 seconds. But here's the deal. If you've ever had a hot cup of coffee, 100 degrees is too hot to drink. 100 degrees Celsius. 100 degrees, or 50 degrees Celsius is still too hot to drink. So it's down here, about 30 and 40, because 30 is like 100 degrees Fahrenheit. Actually, 37 is more like 100 degrees Fahrenheit. And so here, below 50 is where it's starting to get to the point where you can actually drink it. But that's assuming, you're in a non-insulated cup and all this stuff. But what I'm trying to say here is that things rapidly cool, but now that they're down to like, let's say 40 degrees Celsius, well, now that time is going to really start extending. Because to get from 50 to 40, that was almost another 10 seconds there. And then to get from 40 to 30, that was another 15 seconds. And then 30 to 20 is almost 30 seconds. And so here to actually cool off to room temperature, it's going to take a lot longer. So you'll notice they go from like, say, 15 degrees Celsius to 10 takes like almost 2 minutes, whereas it took like 15 seconds to drop 40 degrees at first. And so that's what Newton's law of cooling is saying, is that the greater the difference in the temperature of the two objects, the quicker they change. So once they get close, it'll still continue on to change. It will just take a very long time. Does that make sense? So here, there's a lot going on this side. Don't panic, it's really not that big a deal. So our law of conservation of energy says that energy is neither created nor destroyed. So that's not new. Okay, that's from the last unit. So if you change it from one form to another, that's fine, it's just always going to be there. So all we're doing here is we're adding on energy here for the thermal energy. So we can have our potential energy and our kinetic energy, but we can also have heat energy as another form of energy that can be transferred in. And so like when we talked about like the pendulum swinging back and forth, and I showed you, okay, here we're swinging this pendulum along, and eventually the pendulum will stop swinging, right? That's because friction is taking the energy away from kinetic and potential, but it's taking it away and it's giving it to heat, right? And so heat energy is always going to be, you know, one of those things. And so the total energy is always conserved. So here we're looking a little bit further than just mechanical energy. And so we say the total universe, the total energy in the universe remains constant, as far as we can tell. So now we're getting into the laws of thermodynamics. And one of the first law of thermodynamics is basically a restatement of the law of conservation of energy. And one of the biggest takeaways from the first law of thermodynamics is that heat and work are the same thing. And so remember, we talked about work, that like as the transfer of energy, you have to push the car in order for it to get more energy. Well, it's the same deal with heat, that it's a transfer of energy. And if you're not physically transferring the energy, if the object isn't different after you push it, then there is no transfer of energy. So it's the same thing here. So, for example, a good example of using heat to do work or work creating heat is you can just rub your hands together, right? If you rub your hands together, that creates friction, and that friction, well, increases the temperature of your hands. And so you're doing work, you're applying force over a distance. That's work, and you're creating heat. If you take a nail and hammer it into a board, and then pull that nail out very quickly, the nail will be very hot, right, because of the friction between the nail and the board. So mechanical energy, kinetic, and potential is conserved when there's no friction. The total energy, including the internal energy, is always conserved, okay? So this is the first law of thermodynamics. There's actually 4 laws of thermodynamics, but we're going to focus on the first 2. But we'll cover all of them here, just so that we make sure that they're covered. So the first law of thermodynamics is, like I said, it's a restatement of the conservation of energy. It's right here. It says the total increase in the thermal energy of a system is the sum of all the work done on it and the heat added to it. So if you're trying to figure out how much energy this system has, internal energy, thermal energy, sorry, the thermal energy change, it's simply going to be the whatever work you did on it plus any heat you added to it. So really it's just saying that energy can't be created or destroyed. So again, it's going to be difficult for us to calculate an increase in internal energy. We can do work on a system, which will increase its internal energy, or work can be done by a system, which would decrease its internal energy. So, what does that mean? So it gives us an example. You have 100 joules of gas in a car, but it doesn't move, versus 100 joules of gas in a car that does 55 joules of work. So if you have 100 joules of gasoline in the car, and it doesn't do anything, well, in the end, you still have 100 joules of gas in the car. But if you have 100 joules of gas in the car and it starts to move, and does some work, there's 55 joules of work, well, you can say, well, what's my total energy? Well, it's still 100, but 55 joules of work, was used to make the car go forward, which means you would only have 45 joules left in the gas tank. Like that. law of thermodynamics says that, it summarizes heat cannot pass from one body to a hotter body. The second law of thermodynamics, and most of the laws of thermodynamics are extremely obvious. It says, an object, the heat passes from a hot object to a cold object. This is, again, it's a law, but it's based on our observations of the natural world. And again, you guys know this. If you have cold ice cream and you leave it out on the counter, well, it's going to melt. The heat from the room is going to warm that ice cream. And again, if you have a hot cup of coffee and you leave it on the counter, well, it's going to cool off to room temperature. The heat's going to go from the hot coffee to the colder room. So that is just the way things naturally go. Whenever you convert energy from one form to another, you always lose some energy as heat. Even if you're using heat to do work, so that heat energy will be lost as waste heat. Because of this, whenever you convert energy from one form to another, you can never get 100% perfect energy transfer. The second law of thermodynamics has some very large and far-reaching consequences. One of the easiest to grasp is, think about this. I know it's not summertime, but most of y'all have been through a Texas summer, right? It's kind of hot, isn't it? I remember when I was in school, I used to think, well, it's really hot outside, but it's nice and cool in my house because the air conditioner's running. So my brain thought, well, if everyone's got an air conditioner on, if we all just open our doors, that'll just cool everything off, right? You could try, but it's guaranteed to fail. And the reason why it's guaranteed to fail is because of how an air conditioner or your refrigerator works. They're heat pumps. They pump heat from one place to another. So for instance, your home air conditioner takes the heat that's inside your house and pumps it out. Like that outside unit you have attached to your house. If you've ever been around it, when it's running, you're not crazy. It is hotter next to that because it's dumping heat. Where is it dumping the heat? Well, it's dumping it outside. If everything was 100% efficient, the energy you were using to pump the heat from inside to the outside would just end up moving all the heat outside. That's at best keeping the total temperature or total heat the same. Does that make sense? Because you're just moving from inside your house to outside. But because of the second law of thermodynamics, no energy transformation can be 100%. That means that while your air conditioner is running, it's making its own heat. That's actually not just dumping the heat outside, but creating heat on its own. Thus making the outside even hotter than it would have been without your air conditioner. So hopefully you guys can see that it's going to be physically impossible for us to cool the world by using an air conditioner. Because we have that extra heat that's going to be generated when you're running the motor. And that's always true. So here, this kind of talks about how a refrigerator works. It's the same as your home air conditioner. I'm not going to get too much into these. You can look at these on your own, or you can ask me questions if you want. But essentially, it's just a heat pump. Essentially, what's happening here is, in any of these things, you have a compressor which compresses the liquid in the line, and so you have some sort of coolant. It used to be Freon, although that's illegal nowadays. But it's some sort of coolant or refrigerant, and what happens is essentially it's a transfer between like liquid and gas. And basically, when a liquid is a liquid, it has less thermal energy than a gas. And so you allow it to expand, and when it expands, it will give off this heat in its gaseous form. And then you can use the cooled liquid in your refrigerator or freezer to cool off the objects in there. So basically what happens is you have the liquid which absorbs heat from inside, and then because it absorbed the heat, it turns into a gas, so you let the gas go outside the fridge to dump. So most refrigerators, this is really an old picture because most refrigerators don't have the cooling unit on the back anymore, it's usually underneath it. Which is why, like, if you're ever in the kitchen, you'll notice that the floor underneath your fridge is a little bit warmer. I'm not going to get into the hot water heaters, but it's the same kind of concept here. Again, you want to, this is talking about convection, you know, rise high or rise cool, they're saying it's because they're less dense, right? They're less dense because those molecules won't move around. And I'm not going to get into all that. So here's a question. It says 4 containers are filled with warm water. Which container would have the warmest water after 10 minutes? So they're all filled with the same temperature water. And we have 4 containers. We have a shiny metal, a dull black metal, and a shiny black metal. And so if you have, let's say, a light shining on these things, which one's going to heat up the most? So it really depends on if you're thinking about heating or cooling here. So the shiny metal container would have the warmest water after 10 minutes because its shiny surface reflects the radiation waves back into the container, meaning less heat is lost. So this is shining on the inside. The dull black metal would be the coolest as its surface is best at emitting heat radiation. So here we're thinking, I think I misstated it. We're thinking about just the water cooling off. And so, you know, the lighter, or you can think like white, is going to be better at reflecting radiation, so that's kind of like the shiny here. And like the dull black is going to be best at radiating heat. So when you think about it, like if you think about, like, say, cars in the parking lot, they're all pretty shiny, whether they're black or white or whatever. So we don't have to think too much about the shiny part. But if you're thinking about your car heating up or cooling off during the day, which car tends to be warmer, a black car or a white car? Black. And so black cars tend to heat up quicker. Now, what's interesting about black cars is they actually tend to cool off quicker as well. Which, you know, most people in Texas don't think about too much because we just think, oh, it's hot and terrible. It is, but it's going to be harder to cool that white car because of its reflecting the radiation back into itself. Hopefully that makes some sense. Do you have any questions here? So now this is the same question, but this is an absorption experiment. And so it says, now you're shining a light on them. Which one's going to be the warmest after 10 minutes? So the dullest black would be the warmest because it's the best at absorbing the radiation. And the shiny metal would be the coolest because it's best at reflecting. So it's the opposite if you're looking at absorption versus emission, which is kind of what we said. Okay. So which of these is not a form of heat transfer? Radiation, insulation, conduction, or convection? Which of the following are not particles? Which of the following are particles closest together? So we're talking about those molecules moving: solid, liquid, gas, fluid. Solid. Easy. How does energy reach the Earth from the sun? All right. The last one's radiation. This one says, which surface is best at reflecting heat energy? Shiny white, yes. Good. Which is best for absorbing heat radiation? When two objects come in contact, the heat energy moves from the hot object to the cold one until thermal equilibrium is reached. Okay? Depending on the two objects' composition, the heat will transfer differently. Right? Because again, that goes back to the specific heat. So here we're talking about thermal conductivity versus specific heat. So thermal conductivity is how quickly heat can pass through a material. And then specific heat is how difficult it is to heat a particular material. And so they're similar, but they're different. Like specific heat is asking how much energy it takes to actually physically heat this up. And thermal conductivity is how quickly you can pass energy through a particular material. So obviously, things, they kind of go hand in hand, because if it's a good conductor of heat, well, it's going to have a low specific heat. It's going to be easy to heat up and cool off. All right, so the second law of thermodynamics, it says that heat always goes from a hot object to a cold object. And I said it's one of those things that has very large and far-reaching consequences, and this is one of them. We define a thing called entropy. Okay? Entropy means disorder or chaos. Okay? Now, if you look up entropy online, there's an actual symbol for it. You can actually calculate it in any given system. We're not going to calculate it. Okay? I just need you guys to know the definition and how that might apply to your lives. So, what this is saying here is entropy is a measure of disorder. And because heat transfers from hot objects to cold objects, what that means is that entropy or disorder always increases because we always lose some energy as waste heat. So think about it like this. If you had a cup of coffee, it's got a bunch of molecules in it running around. Let's say it's got 10 molecules moving around really fast. Well, as they cool off, they're going to bump into the cup, they're going to bump into the air around them. They're going to give that heat energy off. And so we say it's very orderly when all of the heat is in the cup because it's just in one spot. Does that make sense? But over time, the heat will leave and enter the room. So now it's the same amount of heat, but instead of it all being in this spot, it's everywhere in the room. And it's more chaotic. So think about it like your clothes. If all of your clothes were put away in your dresser nice and neat and folded, that's nice and orderly. But if you take those same clothes and you throw them all over your room, it's the same amount of clothes, right? But is it nice and orderly anymore? No, it's all chaotic and disordered. And so what this is saying here is that because of the second law, because you always lose some energy as waste heat, things naturally go from ordered to disordered over time. So literally, if you think about it, think about your lawn. You know, like in the fall, like all the leaves come off the trees, and your parents say, go rake up the leaves or whatever. If you go out in the forest, does anybody rake up those leaves? No. Because the forest isn't all nice and neat and clean and trimmed and all that. It's just all chaotic and disordered. Because that's what happens in nature. Life creates order, and then as life dies off, it just creates more disorder. And so entropy is just natural. And, when next time your parents tell you clean your room, tell them, I can't find entropy, Mom. But this actually this is the biggest consequence of the second law, is that things just naturally become more disordered and more chaotic because the energy is getting more spread out. What that means is eventually it will cause the entire universe to die. So, with each transformation of energy, the total amount of useful energy is lower. Because remember, every time we change energy from one form to another, we're always losing a little bit of waste. It's this waste heat. And so every energy transformation, we can change it as many times as we want, but as long as we're always losing some, it's always becoming more disordered and more chaotic, you're always going to tend towards disorder. So, example, your room. Think about your room. Like, when your parents tell you to clean your room up, you're like, oh, I go through all this work, and you clean it all up, and you get it all nice and neat. It should feel nice once you get your room clean, but it takes a lot of work to do that, doesn't it? Does it take a lot of work to make your room messy? It just kind of happens. It's like, oh, didn't I just clean this up? Because that's entropy, that's disorder or chaos. So here, this is talking about changes of state, which you guys should really know. But I'm going to re-emphasize it here because goes along with that kinetic molecular theory. Think about the molecules just moving faster. In a solid, they're moving so slow that they can actually bond with one another. But then you heat them up a little bit, and they start to move faster. And now we have a liquid. Then you heat them up even more, and they move faster. And now you have a gas. And it turns out if you heat them up and they start moving even faster, you can get what's called plasma. A plasma is just like a gas, except, like if you think about it going from like a solid to a gas, where a solid had, you know, if you think about an atom with its nucleus and all its electrons whizzing around it, that's bonded to an atom next to it because they're not really moving. But as you move faster and faster, then these two things can't bond anymore, and you have your molecules whipping around individually. Well, like a plasma is where the molecules are moving so fast that the electrons cannot stay in orbit around the nucleus. So if you have something that's hot enough to be a plasma, you have the positive nucleus flying around completely free, and the electrons just flying around completely free. Like they are still attracted to each other, because positives and negatives attract, but they're just moving so fast they can't stay next to each other. And plasma is what the sun is made of. Here, this is an adiabatic process. This is the definition of adiabatic process. It's compression or expansion of a gas without heat entering or leaving the system. And this is how a car engine works. So if you don't know, here's a short overview. The piston in a four-stroke engine, which is typical of what most of your engines are. In a four-stroke engine, the first is the intake stroke, so it pulls down and it brings in gas and fuel, so air and fuel, in here. And then the second stroke is the compression stroke, so the piston goes up and compresses that air-fuel mixture. And so as soon as this thing starts to go up, it closes this valve so nothing can come in or out. Then at the top of the compression stroke, the spark plug fires and causes a small explosion inside of your car, and then that explosion forces the piston back down. This is the power stroke. And then at the end of the power stroke, this exhaust valve opens and the piston comes back up, forcing the burnt air and fuel out, to go back in your car. And then when this gets up to the top here, that valve closes and the other valve opens and the process starts all over. And so in your engine, if it's a four-stroke engine, only one of the four strokes is actually producing power. But a typical gas engine is what we call a heat engine. It's running off of the heat from this explosion. And so when we talk about heat doing work, well, we're using heat, we're making this little explosion do work. We're applying a force to force the piston down over a certain distance. And if you know anything about engines, you know that there's some things called like the bore and the stroke. So like the bore is like the size of this circle here for the piston, and the stroke is how far down it goes. And so you can use stuff like, how large the stroke is to calculate the actual power output of the engine. Let's talk about the ideal gas law. I'm not really going to get into that. It's more chemistry and whatnot. But I do want to point out this, that like this engine, like the internal combustion engine, first of all, it's an internal combustion engine with tiny explosions occurring in your car. That your car is powered by tiny little explosions. And that's all based on, laws of thermodynamics. Is that the end? Looks like the end. Okay. So, that's the end of the notes. So we're done with that for today. Do you have any questions?
Wait,
But,
so you said the burnt air and fuel goes out of your car. I thought cars were supposed to like liquid and stuff.
what do you mean leave liquids?
Like, I don't know, sometimes I'll see your car, like driving down the road and it's got, like from the exhaust pipe it.
Oh, it's dripping? Oh, that's just condensation.
Oh.
Because what happens is, like, at night, when your car is off,
Yeah.
like the air from outside will kind of like go up your tailpipe and whatnot,
Right.
and it'll be cool, and then when you start your car, it'll force all that water vapor out, and so that's all it is, just water vapor.
What about the burnt fuel? Where does that go?
Into the atmosphere.
Oh.
That's one of the reasons why we have, like, pollution.
Cool.
Because Most engines do pollute. Different engines pollute by different amounts, but think about it like, I mean, that's the whole deal with like global warming, and we're talking about, you know, carbon emissions and stuff like that, because gasoline is a hydrocarbon. I'm not going to get into it too much, but it's a hydrocarbon, and so when you burn it, you release that carbon as part of